Hello and welcome. I'm DDCOM from Malvern Panalytical, and today I will be talking about the DDCOM desktop crystal orientation diffractometer, which we have over here. The DDCOM works by the Azimuthal scan method. In the Azimuthal scan method, we place the crystal on the table here and put the detector and the tube to one fixed angle. Then we rotate the sample at least 360 degrees. We pick a diffraction angle so we can record planes that are not perpendicular to the surface. So if this is my crystal and we're measuring the 001 main direction, what we actually will be recording are, for example, 111 planes here. Yeah, as you can see from this model, they will only show up at exactly the right rotation angle. By measuring when they show up and how far they are spaced apart, we can find both the tilt of the crystal, the tilt direction, and also just about every other direction within the crystal. Okay, so the DDCOM itself. We have it here. It looks a bit empty, and compared to our other systems, there is less going on. For example, we do not have any laser sensors. In the DDCOM, we have our tube and detectors under the table here. Yeah? Samples get placed up here. The sample just needs to be big enough to cover the hole and needs to have one flat side. Since the goniometer doesn't actually move and the sample is always in the same place and we're always measuring the bottom of the sample, there's no height alignment, so you can just place the sample and start measuring. To help us, for example, measure wafers or boules we're trying to put a flat on, we have this stop that helps you align the crystal, which can be moved in or out and locked with this handle here. These metal parts also help you align larger wafers exactly, so you can repeatedly measure the orientation and also the in-plane rotation very well. One of the advantages of the DDCOM is that it can work with just a 30-watt tube. Yeah, we have a very low-powered X-ray tube. That means that the only requirement for the DDCOM is basically some household power outlets for the DDCOM and for the PC nearby. We don't need anything like cooling water, any gases, or anything like that. Okay, so because we only measure a flat side, this is also very great for irregular shaped samples, and we can very quickly measure. So if you are measuring at a line, yeah, you're going to do your epitaxy experiments or production, and you need to once in a while check a wafer that is somehow a bit suspicious, or you just check it routinely, you can just place it on here, select the recipe, press start, and you'll have your result in as little as 10 seconds. So DDCOM also has quite a few options to equip it with different rulers and marking systems, which would be mounted in the back. We don't have them mounted here. We can also replace this flat stop with a notch stop. Yeah, we can see here how it works. There's just a lever that locks it into place or not, and we can very easily switch it over. These can also be made to different lengths. We can accommodate different types of samples that way. Now let's try to actually measure a sample. Here we have our silicon carbide wafer, which we'll use for our demonstration now. And I just go and place it on a table, push it carefully against the stump, close the system, go to the PC, and then I just press start. Now the system is measuring. It does one lap to warm up, which is 5 seconds, then one lap to measure, another 5 seconds, and there, now we have our data, 1 more second to calculate, and now we have our result in about 10 seconds, and this is the quickest result you can get. If you want to be more accurate, you could add more rotations and you get more precise. From this quick measurement, we get the tilt and the tilt direction here in numbers and over here in this diagram. So we see the reference axis was O-10, which was facing the stop. And here we have a drawing of the tilt. So it was 4.19 degrees towards the 2-1, 0 direction. And the main direction is 0, 0, -1. And we can see all these other directions in the crystal because we actually did not measure one reflection, but we measured 6, as we can see down here. Yeah, we have a 6-fold symmetry. We see 6 peaks. They are about the same height, and they are about 60 degrees from each other. That's about as far as you can interpret this by eye. That looks fine. And in the other detector, we see almost exactly the same thing. So this is all. We can tell this measurement is fine. Besides the tilt and tilt direction, we also get the ref offset. Yeah, that is the angle between the reference axis and the stop we are using. We also have comp0 and comp90. These are the Cartesian representations of the tilt, which are sometimes very easy to just copy over into a grinder or CNC machine to mill, for example, a flat block of crystal for optical purposes. Okay, and that was the silicon carbide sample. Now let's go measure something different. First, I need to put away our wafer. And then I've got this calcium fluoride octahedron, which has flat faces, but they are not exactly parallel. It's not a problem in this case because we can measure anything that has a flat side, and we'll cover the hole in the middle. Just place it on here. Close the doors again and go back to the PC. All I need to do to switch materials is pick the calcium fluoride recipe out of the list here, change over the name, and again press start. The goniometer adjusts to the correct angle, and the stage starts spinning again. One warm-up lap, one measurement lap, and there we are. So this time we see that we have 3 pairs of peaks, so 3 per detector, which makes sense. This is a cubic 1-1-1 direction, so it has a 3-fold symmetry. And again, we get the results in numbers. The tilt in this side is 1.035 degrees. We have a tilt direction. We have a reference offset. In this case, I did not align it properly to the stop, so this is not as meaningful as normally. And we have the reference axis, which is 1-10. And here we have the whole thing graphically again. It's very easy to also measure somewhat more irregular shaped samples as long as they have one flat side at least. So that was our introduction for the DDCOM. As you can see, it is a compact and easy to use desktop diffractometer for crystal orientation. It measures very fast because we do not need height alignment and use the Azimuthal scan method, but we can provide a very high accuracy while it's also very easy to use.